pe con la veo nahe o kapilina kaua o kapilina me con la veo nahe o kapilina kaua o kapilina
I'm going to begin. It gives me great pleasure today to introduce the speaker. I've often said one of the greatest joys for a faculty member is to introduce their graduate student for defensive dissertations. And today we're all here to hear Anna Babakarman talk about her work on adequate responses to Bar 2 CSA in pregnant Cameroonian women. Now, I thought it was rather interesting that Anna picked out this background of the world. And at first I wasn't too sure why, except that Cameroon was right in the middle, and the center of our universe and our lab. Then I realized this is very reflective of Anna because she's a citizen of the world. As you know, she has spent her youth in Russia, Armenia, and Georgia, which, by the way, have 3 different languages. She then, while in college, came to California, which is about 1,500 miles off the map, and then to the University of Hawaii. And in August, she will be leaving us to go to Cameroon. Through her history is that she completed a master's in biotechnology at San Jose State University before coming here. And she was interested in 2 things, stem cells and global health. So she applied to graduate programs. University of Hawaii offered her a scholarship from the dean. So she came to our department in August 2010. She joined our department in global health. And I think that was a really smart move because she has decided she really wants to spend the rest of her career studying global health. She was here a very short period of time before she passed her comprehensive exam. She then went to a workshop in Cameroon. She completed her coursework and passed her qualifying exam. She didn't pass the same exam twice. She passed her qualifying exams, and then she applied this last fall for a postdoctoral fellowship in global health fellowships. And much to our delight and surprise, she was awarded this fellowship. And I say surprise because these are extremely, extremely competitive fellowships internationally. And so when she got one of these, it was really a real coup. And like I said, she is now presenting her dissertation research to you all. Anna joined her department at a time when we look at the top. The little girl in the blue is Dr. Young-Lo Totaro, who was working on Bar 2 CSA. And they overlapped by about 2 semesters. And so Young had an extremely good committee. And so we kept the committee to follow on. Young taught Anna, trained her well for the first year, and but then after that, Anna took over the project and made it totally her own. Today I'd like to thank our committee, Dr. George Hui, who is an expert in the immunology of malaria, Abby Collier, who is an expert in placental biology, Wei-Kung Wang, who is an expert in mapping of B-cell epitopes and thinking about vaccine development. John Chin, you'll see mathematical modeling, you'll see how that comes in. And Dr. Paul Paddock, who is our outside committee member, who is an immunologist and knows now a lot about works with CSA. Anne has worked very hard in the laboratory while she's worked here. You have to work hard to complete a PhD in 3 years. She has worked with some really wonderful people in the laboratory who's taught her about malaria. Because she came here, she knew nothing about malaria, and she knew nothing about immunology. She's getting a PhD in the immunology of malaria. So. Now, Anna's worked very hard, and not everything has worked. For those who know, this is a Luminex-based assay. The green means it works, the black, the red says it didn't. So she's had some failures, but that has allowed her to be extremely happy when experiments have succeeded. Anna was able to spend a short time in Cameroon, and suddenly the idea of intermittent preventive treatment and the use of insecticide-treated bed nets and rural environments became reality. They were no longer serum samples and things she read about in textbooks, but things that she certainly began to understand and appreciate. This is some pictures of Anna in Cameroon. You can see her sitting there on her compound step, but you can see she quickly made friends. And she learned how to bring home bread from the bakery in the blue bag. She then met a variety of other Cameroonians who are here today as part of our global infectious disease. And she was very helpful in helping them apply to graduate school here. She instantly bonded with Alvine, the young woman you see in the top picture, but unfortunately she did not receive a visa and could not come for the PhD. But wherever Anna was, you can see she was surrounded by kids who really found her lovely. So we're excited for her to be able to go back to Cameroon. This is perhaps one of my favorite pictures. This is Professor Robert Leckie. We are in his home village of Minchi, and he is introducing them to village women. So she began to understand and began to talk to people who live in rural environments. Over on the right, it's called Women Empowerment in Family Center. And Cameroon has a strong sense of movement for empowerment of women. And I know Anna is going to fit in very well when she goes back next year because, A, she's a woman, but 2, because she's studying global health diseases that influence women's health. And I know she'll be very appreciated. And I can't help but think this is one of my favorite pictures because Anna is favorite for her pink shoes, which you've seen in 2 pictures, and I think you're going to see some today as well. Anyway, Anna, we wish you the very best after you leave here. We hope from all those in the laboratory, we wish you the best. And after all, don't forget us. So without further ado, I introduce you to Anna Babakahanyan.
Dr. Taylor, for a wonderful introduction. I'm really humbled to see all these pictures and all the work you put together, besides everything else, of course. But today I'm here to tell you about all the exciting results. They're exciting because 1, they work, and 2, I think they're important for providing better health care to mothers and their children. I'm going to talk about my results on antibody responses to malarial Varchus CSA antigen in pregnant Cameroonian women. Malaria today remains one of the big 3 infectious diseases in the world. 33 billion people are at risk of malaria, and 98% of malaria deaths occur in Africa. Every 45 seconds, a child dies of malaria in Africa, and children and pregnant women are at increased risk of malaria. Malaria is the most common preventable disease, and the cost of malaria is actually inexpensive. Thus, it's more devastating to see these numbers of deaths. Burden on malaria is especially severe in pregnant women, and 85 million women worldwide every year are at risk of malaria during pregnancy, with 30 million women living in Africa. And first effects of malaria during pregnancy include maternal anemia, intrauterine growth restriction, premature delivery, fetal low birth weight babies, and in severe cases, deaths. About 1 million neonatal deaths occurred in mothers exposed to malaria during pregnancy. Occurred in children who were born to mothers who had malaria during pregnancy. And malaria is responsible for 14% of low birth weight infants worldwide. Placenta, shown on the right here, provides a new niche for parasites. And that's why women are especially, pregnant women are especially vulnerable to malaria. VAR2-CSA, a malarial antigen expressed on infected red blood cells, allows infected cells to bind to chondroitin sulfate A in the placenta and results in accumulation of these cells in the placenta. Accumulation of infected cells in the placenta causes a condition known as placental malaria. And in this condition, nutrient and oxygen transport across the placenta is reduced, and therefore it leads to low birth weight babies. Also, it is difficult to diagnose malaria in pregnant women because the infected cells accumulate in the placenta and are not found in peripheral blood. Well, fortunately, vaccine for placental malaria is feasible, and VAR2-CSA is a leading vaccine candidate. Antibodies to VAR2-CSA are important in protecting pregnant women from placental malaria, as they inhibit binding of infected cells to the CSA in vitro, they reduce maternal anemia, lower placental parasitemia, and increase the length of gestation and improve overall infant birth weight. This protein is very immunogenic, and high levels of antibodies to VAR2-CSA have been found in multi-gravid women, or women who have been pregnant for several times. It's present on the surface of infected cells for prolonged periods of time, and antibodies to VAR2-CSA are strain transient, meaning these antibodies can bind to parasites isolated from different parts of the world. And recombinant constructs of this protein are now available. So currently, VAR2-CSA-based subunit recombinant vaccines are under clinical evaluation, and this approach was chosen because antibody-mediated immunity is thought to be the most important mechanism for controlling placental malaria. This figure here shows the structure of VAR2-CSA. It's a large transmembrane protein. It consists of 6 double-binding like domains, domain 1, 2, 3, 4, 5, and 6. And different groups around the world choose different domains for vaccine. So, for example, Seattle Biomedical Research Institute and NIAID consortium that's headed by Patrick Duffy is focused on the C-terminal of the molecule, and they believe that domains 4 and 5 should be included in the vaccine because antibodies generated in rats bind to placental parasite isolates and inhibit binding of infected cells to CSA on a placental tissue. On the other hand, European consortium headed by Alice Alanti at the University of Copenhagen recently received a grant for their first clinical trial of VAR2-CSA vaccine, and it is based on ID1 IDTA construct. This construct is actually a minimal sequence that is required for VAR2-CSA molecule to bind to the CSA. And it's shown on my map here. So this is the full-length molecule, and the minimal binding domain encompasses interdomain 1, domain 2, and 83 amino acids from interdomain 2A. Right now, they're in their phase 1 clinical trials. These are safety studies, and their primary outcome measure is side effects of this vaccine. Phase 1A is in Germany on 30 male volunteers, and Phase 1B is going to be conducted in Benin on healthy women on birth control pills. And their secondary outcome measure is to look at the anti-adhesive properties of antibodies generated after vaccination. However, precise region of VAR2-CSA that is important for inducing protection still remains unclear. It seems like one group is focused on domain 4 and 5 at its C-terminus, while the Copenhagen group is focused on the opposite end of the molecule with a minimal binding site. And what's in common between these two groups is that they both hypothesize that naturally acquired antibodies which prevent binding of infected cells are associated with reduction of clinical disease. And therefore, I believe that tertiary structure of recombinant VAR2-CSA subunit protein is going to be very critical. There are some challenges associated with the current vaccine development approaches, and the biggest one is absence of correlates of protection from placental malaria, because there is no way to adequately test the vaccine in humans. And we need correlates of protection to be able to show vaccine efficacy, also to assess immune status of pregnant women on an individual as well as the public level. And finally, the use of intermittent preventive treatment and bed nets, basically chemoprophylaxis and insect-treated bed nets throughout Africa, significantly reduced exposure to malaria, and therefore we cannot study vaccine efficacy. Thus, the overall goal of my study was to define cause of protection from placental malaria. So in my aim 1, I was set to determine if pregnant Cameroonian women naturally acquire antibodies to the minimal binding site and if they correlate with absence of placental malaria. We collaborated with Alice from Copenhagen, and he provided us a recombinant construct. And we hypothesized that antibodies to the minimal binding site are correlated with protection from placental malaria. Well, this is really exciting, and we thought we're just going to have it easy. However, in a few minutes, I'll show you that our hypothesis proved wrong. So we had to go with alternative approach. And in my aim 2, I decided to identify cause of protection using an innovative multi-assay approach. So the basis, our hypothesis is that multiple assays provide data that could more powerfully predict placental malaria compared to a single assay by itself. And finally, in my aim 3, I wanted to use data from aim 2 to see if women who receive IPT-SB, intermittent preventive treatment, as well as bed nets, have preserved this cause of protection during the treatment. So the hypothesis was that the treatment will reduce antibody levels to virtual CSA domains, as well as the quality of response to placental malaria. So in my aim 1, again, I wanted to see whether antibody responses to the minimal binding site correlate with protection. So just a reminder, minimal binding site is this small part of small domain at the end terminal of the molecule. Minimal binding site was shown to induce antibodies in rats that inhibit binding of infected cells to the CSA by nearly 100%. Also, because the peptide is small, it can be used easily on for large-scale production. And we wanted to determine if pregnant Cameroonian women produce antibodies to the minimal binding site in response to the natural infection. So just to point out that this is a recombinant peptide or molecule, and we wanted to see if naturally women recognize this part of the virtual CSA. And also we wanted to know whether antibodies to the minimal binding site correlate with protection. So for the studies, it was conducted in Cameroon, and in Cameroon, malaria is transmitted year-round. We chose 3 study sites, the capital of Cameroon, Yaoundé, where malaria has low transmission, and this is our clinical team in the city, basically with the patient. And we also included 2 rural villages where malaria is transmitted, has a high transmission, and one of the villages, Mugalitu, is presented on the screen. So all the samples, archival samples used in the study were obtained before IPT and ITN implementation. So the antibody responses we're measuring were not affected by the chemoprophylaxis and bed net usage. So a total of 727 plasma samples from Cameroonian pregnant women were screened, as well as 136 Cameroonian males, 42 US pregnant women, and 25 US non-pregnant adults for comparison. And we measured antibody levels to the minimal binding site that was produced in 2 malarial strains that was donated by Alice from Copenhagen, as well as the full-length molecule for comparison. And this, we used multi-analyte platform assay, which allowed us to have a high throughput assay where we measured antibody levels to 14 antigens in 1 well, and it required only 1 microliter of patient blood. So in the assay, we coupled recombinant proteins to the microspheres and then incubated with plasma that we obtained from pregnant women. After several washes, we incubated with secondary antibody, and then we read the results on Lumen X100 reader. These are my results, and I'm showing results only for Ngalitu village, where malaria has a high transmission, and the patterns are similar for the other locations as well. So first, I want to talk about full-length virtual CSA, because we already have established picture of what's going on with full-length virus CSA. So males from Cameroon are shown in blue, primigravida are shown in pink, and multigravida are shown in purple. So, since virus CSA is pregnancy-specific antigen, antibodies to virus CSA should be present only in pregnant women. And pregnant women or primigravida who are pregnant for the first time experience primary immune response, whereas multigravida have seen the antigen previously and now have secondary immune response. So the data is shown for antibody levels in males as well as primigravids and multigravids throughout pregnancy in the first, second, and third trimesters. And we can see that antibody levels are very low in males, or almost they don't have any antibodies. Whereas in pregnant women, we see high antibody levels, and they increase during pregnancy. So like I said, the women did not receive intermittent preventive treatment. Therefore, they were exposed to malaria during pregnancy and became infected and had higher antibody boosting. So we expected to see something like this, similar response for the minimal binding domain, maybe at the lower levels, but still the same pattern. However, this is what we see we obtained for the minimal binding domain. So again, males shown in blue and primigravida and multigravida are shown on the right. And you can see that antibody levels to the minimal binding site were the same across three groups. So they were present at equal levels in males, Cameroonian, primigravida, and multigravida. And the results were very unexpected. So we hypothesized that some cross-reactive epitopes must have been present on the recombinant minimal binding domain, which are not present in a full-length conformation, because as you can see here, the antibody levels to full-length in males are almost non-existent. So next, we wanted to see if this cross-reactive response could be seen also in the US adults and pregnant women, because if those cross-reactive epitopes could be to other malarial antigens or any other pathogens in general. So US non-pregnant women are adults are shown in white squares. US pregnant women are shown in black squares, and the rest of the categories are the same. So these are antibody levels at delivery to the minimal binding site. As you can see, antibody levels to minimal binding site are absent in the US population and being present at equal levels in Cameroon. So this is, these responses are associated, or cross-reactive responses are detected only in Africa, more specifically in Cameroon. We next look at the prevalence of individuals who had antibodies to the full-length virus CSA, shown in dark blue, as well as the minimal binding site, shown in light blue, in males, primigravida, and multigravida. As you can see, prevalence of men who had antibodies to the full length is almost like 5%, compared to women who had 70% in primigravids and 90% in multigravids. When you look at the prevalence of individuals who had antibodies to the minimal binding site, about 90% of individuals had antibodies to minimal binding site across three groups, again showing that this is non-pregnancy specific antigen. Since this is the vaccine candidate, we wanted to confirm these results in some other assays. And we know that cross-reactive antigens may elicit antibodies with low avidity, and therefore we measured avidity to the minimal binding site, hoping to get rid of some of the cross-reactive response. However, no difference in antibody avidity to the minimal binding site was found between males and Cameroonian females. And when we look at antibody avidity for the full length, we saw statistically significant differences. Next, we saw that the minimal binding domain could be poorly immunogenic, or it could use IgM to mask protective IgG epitopes and therefore evade immune system, which was shown for several other pathogens. So we measured IgM in our subjects to the minimal binding domain, and our results demonstrate that women and men produce IgM at equal levels to the minimal binding domain, and there was no evidence that IgG switching was impaired. Those antibodies to the recombinant minimal binding domain produced in response to the natural infection are not pregnancy associated and do not correlate with protection from placental malaria. This brings also into question the vaccine that is in clinical trials right now, and we still believe that it could be possible for the vaccine to work because it could induce an alternative mechanism of protection. However, that mechanism doesn't exist in after natural infection. So since AIM-1 didn't work as expected, we moved to an alternative approach. And here we wanted to use multi-assay approach to define cohorts of protection from placental malaria. We know that naturally acquired immunity to malaria in general is through gradual acquisition of antibodies to variant antigens that are expressed on an infected cell surface. And hypothesis that we had was that multiple assays measuring antibodies to VAR2-CSA domains, its strain variants, antibody avidity to VAR2-CSA, as well as antibodies to other malarial antigens, such as AMA and MSP1, used in a multivariate model would be a better predictor of placental malaria. So we had a unique study design because we included pregnant women with 3 or more pregnancies. And the study was conducted in Yaoundé 1, where malaria has a low transmission. And women in this area gradually acquire immunity over many pregnancies to placental malaria. And this study design allowed us to delineate 5 immunological differences between those women who had placental malaria and those who didn't. This study was possible because we used archival plasma samples. Like I said, IBT, chemoprophylaxis, and bed nets confound immune responses to malaria, and basically we cannot test our use of archival plasma samples allowed us to circumvent this problem. And we also had a panel of VAR2-CSA full-length molecule as well as all of its domains that we obtained through collaboration with researchers across the world. And this allowed us to study immunity to placental malaria in a more comprehensive manner. Our study design, again, was in Yaoundé. Some pregnant women were recruited into the study shortly prior to delivery, and peripheral blood samples were collected at delivery. Our original study had 2,500 samples, and we chose all multi-gravid women who met inclusion criteria and had placental malaria, and that's N equals 160. And then we chose 3 times the number of placental malaria negative women randomly from this pool of women. And our inclusion criteria included women who were exposed to malaria, women who were at least 20 years of age, and who had at least 3 pregnancies. So we used the samples and screened them in 24 different assays. And these are the list of different assays we conducted. So we measured antibody levels to all of these domains expressed in different malarial strains, which is 15. We measured antibodies also to the full-length molecule and antibody avidity to the full-length protein. Antibody avidity reflects the strength of antibody binding to its antigen. We also estimated number of domains and variants recognized, and we look at the presence or absence of antibodies to the full-length molecule as determined by male mean plus 2 standard deviation as a cutoff. And we also look at presence and absence of high avidity antibodies to the full length, and we define it as more than 35% antibodies should be high avidity. Like I said, we believe that non-pregnancy associated antigens are also important, so we have included them in our models. So this is amount of boxes I had to generate for all the dilutions, total of 1,700 dilutions, and this generated about 12,000 data points that I had to analyze. So because the analysis was enormous, we collaborated with John Chen and Miao Wang from JAPSOM Statistical Core, who helped me with my statistical analysis. So for antibody levels, so for analytical plan, we took the 24 assays, and first we look at them one by one. So we compared women who had placental malaria and those who didn't for each of these assays. And we used simple unpaired t-test and Fisher's-Digsdale t-test. After that, we did univariate regression analysis for each of the assays, and we generated receiver operator characteristic curves as well as determine areas under the curves for each of the assays to measure sensitivity and specificity of the assay. And then we did pairwise comparison analysis, and we basically end up with 276 pairwise models. Based on the data from the preliminary analysis, we selected some assays that had good scores in univariate models, as well as some assays that had biological relevance. And then we included them in multivariate regression models and an alternative approach, which is called recursive partitioning, that I'll talk about later. So these are results, characteristics of study participants. And basically here, the table shows that the two groups that we used, placental malaria positive women and those who were negative, were really representative of our bigger study population. Of interest, women who were placental malaria negative were a little bit older and had one more pregnancy, and this data was used to adjust our models by gravidity. Also, here we showed that placental malaria increases risk of having anemia at delivery, as well as